Alright, so let's begin today's lecture. Today's lecture, the topic is called Return-Oriented Programming, or is short for ROP. So what is return-oriented programming? Right. So in order to talk about this, we need to first quickly review one concept that we learned from our previous lectures. Okay. Remember that in our previous lectures, when I showed you this Stack Overflow attack, I said that when you compile your code, you need to type the following command, right? So GCC is actually the compiler's name, and then we use these tools to compile the files. -M32 is try to compile this code in 32-bit mode, and we have this no stack protector, which we're going to talk in more detail in the next slides. And then comes this one, right? -Z exec stack, right? So -Z means to disable this executable stack, right? So what is this executable stack means? This is actually related to this the one of the defense or protection mechanisms, and also this protection mechanisms is actually to bypass this protection mechanisms. There goes our today's topics, which is this return-oriented programming, which is a ROP attack. Okay, so let's first take a look at this non-executable or this protection mechanism itself. Right? So this -Z exec stack is basically known as to disable these data execution prevention. So that means if you are not adding this flag, by default, this data execution prevention will be turned on. Yeah. So what is data execution prevention, or short for DEP? This basically just try to protect the region of the memory and then mark those region of the memory as non-executable. Yeah. So remember that back in our previous slides, right? I shows you that in our previous lecture, I shows you that we can launch this Stack Overflow attack. Yeah. So there's actually two types of Stack Overflow attack. If you recall that the first one is called return hijacking attack, which is also your target for the first target for lab 1. And there's another one. The second one is actually much more powerful one, which is this jump to shellcode attack. Yeah. So the jump to shellcode attack, the idea is simply just write this shellcode into the buffer, into a, like say, array, right? And then eventually use this buffer flow to override this return address. As you can see, this time in this figure, at first, when the program asked me to type something, I actually type the shellcode. So there's the shellcode, and then followed by some dummy characters, and then after that, I place the new return address to override the old return address. The new return address is actually been written here, which, as you can see, this is actually we need to convert into this little endian format, which is going to be BFFF0000, right? So BFFF0000 is actually this line, right? This is the memory address. So that means once they finish this function, right? Once you finish taking the user input, they're going to jump to this line, and then execute the code that inside this line. We know that this code is actually the shell code that we inject. So therefore, once the shell code being executed, then they're going to provide us a shell normally, right? So that's well, depends on the type of shell code that you inputted here. All right. So of course you can just read it all this stuff by yourself, right? But you got the idea, right? So this is basically the one that I mentioned, basically the jump to shellcode attack that I teach from our previous lectures. Okay, so the question is there a way to protect this type of attack? As I just mentioned, this DEP, data execution prevention, is actually trying to protect this type of attack by marking this type of memory non-executable. So if we mark this area of memory, this piece of memory, right? I mean the memory inside the stack as a non-executable, then that means if the hiker try to override this return pointer, return address, and then let it pointing to this BFF as 40, there's gonna be a problem because this part is marked as non-executable. So if you try to execute if you try to execute the code inside this non-executable region, then the program will crash, will simply just stop, right? So therefore, the attacker cannot launch this type of attack. So this it's kind of like a very simple solution, right? So because you're about to execute this one, so if in another way, let's think about this again. Okay. All right, so let's begin today's lecture. Today's lecture, the topic is called return-oriented programming, or is short for ROP. So what is return-oriented programming? Right. So in order to talk about this, we need to first quickly review one concept that we learned from our previous lectures. Okay. Remember that in our previous lectures, when I showed you this Stack Overflow attack, I said that when you compile your code, you need to type the following command, right? So GCC is actually the compiler's name, and then we use these tools to compile the files. And -M32 is try to compile this code in 32-bit mode. And we have this no stack protector, which we're going to talk in more detail in the next slides. And then comes this one, right? -Z exec stack, right? So -Z means to disable this executable stack, right? So what is this executable stacks means? This is actually related to this one of the defense or protection mechanisms, and also this protection mechanisms is actually to bypass this protection mechanisms. There goes our today's topics, which is this return-oriented programming, which is a ROP attack. Okay, so let's first take a look at this non-executable or this protection mechanism itself. Right? So this -Z exec stack is basically known as to disable these data execution prevention. So that means if you are not adding this flag by default, this data execution prevention will be turned on. Right? So what is data execution prevention, or short for DEP? This basically just try to protect the region of the memory and then mark those region of the memory as non-executable. Right? So remember that back in our previous slides, right? I shows you that in our previous lecture, I shows you that we can launch this Stack Overflow attack. Right? So there's actually two types of Stack Overflow attack. If you recall that the first one is called return hijacking attack, which is also your target for the first target for lab 1. And there's another one. The second one is actually much more powerful one, which is this jump to shellcode attack. Right? So the jump to shellcode attack, the idea is simply just write this shellcode into the buffer, into a, like say array, right? And then eventually use this buffer flow to override this return address. As you can see, this time in this figure, at first, when the program asked me to type something, I actually typed the shellcode. So there's the shellcode, and then followed by some dummy characters, and then after that, I placed the new return address to override the old return address. The new return address is actually been written here, which, as you can see, this is actually we need to convert into this little endian format, which is going to be BFFF0000, right? So BFFF0000 is actually this line, right? This is the memory address. So that means once they finish this function, right? Once you finish taking the user input, they're going to jump to here, jump to this line, and then execute the code that inside this line. We know that this code is actually the shell code that we inject. So therefore, once the shell code being executed, then they're gonna provide us a shell normally, right? So that's well, depends on the type of shell code that you input it here. All right. So of course you can just read it all this stuff by yourself, right? But you got the idea, right? So this is basically the one that I mentioned, basically the jump to shellcode attack that I teach from our previous lectures. Okay. So the question is there a way to protect this type of attack? As I just mentioned, this DEP, data execution prevention, is actually trying to protect this type of attack by marking this type of memory non-executable. So if we mark this area of memory, this piece of memory, right? I mean the memory inside the stack as a non-executable, then that means if the hiker try to override this return pointer, return address, and then let it pointing to this BFF as 40, there's gonna be a problem because this part is marked as non-executable. So if you try to execute if you try to execute the code inside this non-executable region, then the program will crash, will simply just stop, right? So therefore, the attacker cannot launch this type of attack. So this it's kind of like a very simple solution, right? So because you're about to execute this one, so if in another way, let's think about this again. Okay. So as you can see, this jump to shellcode attack is powerful is because first the shellcode is being treated as a string. So that means when you ask the user to type things, right, like typing things, because we know that they can trigger stack overflow. But when the user typing things, this part of the data is treated as a string. But later, this because we jump to the beginning of this jump to the top of the stack, so this part of the string is later being treated as a code. So this actually the change between string and code gave this a privilege to these attackers. So therefore they can first, let's just type the code, then the code will be executed. So to avoid such privilege or to prevent such type of attack, of course we can simply just, let's say, when you work in this area of the memory, we only treat this part of all this data in this memory as like writable as a string, right? So that means anything that you read in here is not executable, but you can read it, you can print it out, but you cannot execute it, right? So this is this kind of protection is actually being done by so-called this non-execute. This NX, right? So therefore, this protection is actually have two names, right? So in different like website, YouTube videos, they probably just refer it by different names. So sometimes they call that DEP, data execution prevention. Sometimes they call that non-execute, which is short for NX. But both is the same thing. You know, basically just mark this region of the memory. Normally we mean the stack memory as writable but non-executable. Okay. So this NX is this data execution prevention is actually a CPU feature. So that means this is nothing fancy, or it's not being done inside your the code, right? So it's not like say that we can like include some like libraries to do this. Instead, it's actually built in. This one is actually built into CPUs, and they basically just works with this x86 64-bit operating system, or with this so-called physical address extension PAE enable, right? So once you enable this, it will raise an exception if the CPU tries to execute something that doesn't have this NX bit set. And this NX bit is actually located and set up in this so-called page table entry, right? So remember that each process, when you try to run your program, right, they're gonna create a process, right? So they're gonna load this program into the memory, and then we call that, and then they're gonna create a process. Each process in the multitasking operating system runs in its own memory sandbox. We're gonna talk this in more detail. We're gonna study this later in next few lectures, right? So you will have a better understanding when we move on to the next topics. But anyway, so we can say that each operating system, each process is, they thought that they can use up this whole memory space. So the whole memory of your computer. So let's say if your computer have like 4 GB of memory, then each process will thought that they can get access to the all 4 GB. But we know that's not true because there's multiple processes, all of them are currently running, right? So actually, each process can only have limited number of memories, limited memory that they can use. But anyway, we just create this kind of like virtual environment, right? So each process will thought they can use up all this memory space. And then when you create this virtual address space, there is actually a table. You can consider this actually a table to try to write down all this information, including this mapping, how to map this physical memory to this virtual memory, and also for each piece of the memory, they also use this page table to write its privileges. So let's take a look at this page table. So you can see that for each page table, there is for each virtual page, there is a corresponds one page table entry. We call that PTE in the page tables, which in this regular x86 paging is actually simply just 4-byte record. So it's very small, right? This page table entry, only 4 kilobyte. Only 4 byte. So this 4 byte of data is being actually used for storing things, and one of the bit, right? So inside is a page table entry. One bit is actually the very last bit is called this NX bit. Right? So this NX bit can be set as, which is this one, the very last one, this EXP, right? So this one is set to 0, then that means we disable this NX. Otherwise, if it's set 1, then we enable this NX. So as you can see, back to our previous page, right? So in order to set this piece of memory, I mean this stack memory to be the non-executable, all we have to do is simply just find out the page table entry for this piece of virtual memory, and then we set the very last bit of this page table entry to 1. Then that will turn on this protection mechanisms. So anyway, so this part is not that important as long as you know that what this NX or DEP means. That's fine, right? So in short, this DEP or NX means that we just mark this memory space as you can only write things, but anything that write it here can only be treated as data, or in other words, you can just print it, but you cannot execute it, right? It's considered as non-executable, right? So that's the DEP protection. Right, so once we have this DEP protection, then we know that means we can no longer attack this program by launching this jump to shellcode attack, because our shellcode cannot be executed, right? So we thought that's probably the system might be safe, because if the program contains this have this buffer overflow vulnerability, then the only attack that we can use is this return hijack attack. Return hijack attack, just like the one that shows you from our previous lecture, can only allows you to coding certain functions, right? So if there is like a function called hide function, of course we can code that, but we know that normally there's no such backdoor function that exists in the commercial software. So that basically just decrease the attacking surface of this attacker. So the attacker basically if there's no other functions, no useful functions to call, then they cannot attack the software, because this DEP protection has been turned on, right? But the problem is actually after several years, after it's been this protection mechanism been invented after several years, the attacker actually found a way to bypass such protection mechanisms, which is actually the one that I shows as the title suggests. This attack that being used to bypass this data execution prevention, or this non-execute, is called return-oriented programming, ROP. Right? So ROP is like we can use this return-oriented programming to bypass this protection mechanisms. That means we can still, by using this ROP, we can still launch jump to shellcode attack. It's just a little bit tricky, a little bit harder than compared to like straightforward way, like just write it down, but we can still do it. So let's take a look at this the history. Let me give you a brief introduction about this ROP, and then I'm gonna show you how the attacker bypass this protection mechanisms. All right, so the introduction about ROP. So the ROP attack is kind of like relative new type of attack, because you can see that it's actually been published in this is actually a paper that has been published in the academia. So that means the attack has been not first been found by the hacker community, not by the industry, but it's actually from the academia. So that means some schools, professors, and students actually found this type of attack. So the first paper that been published in 2008, in October 2008, which is 12 years ago, quite relatively new, because the Stack Overflow attack, considered that one is actually a very old type of attack, but this ROP is quite new. So the paper title is called When Good Instructions Go Bad, Generalizing Return-Oriented Programming into RISC. And then in 2009, there's actually another paper that been published is called Return-Oriented Programming Exploits Without Code Injection. Right. So both these two papers actually just shows everybody how to launch this ROP attack. So what is return-oriented programming? So you can see from this figure. This figure actually shows you shows you the idea of the return-oriented programming. It's just try to in short, the attacker is just try to launch this return hijack attack, right? So that means they try to changing this direction of the code, but this time, because there's no functions like code hiked, right? So you can not simply just jump to a single function. So instead, this time they try to jump to multiple small functions, which we'll call that the gadget, right? So this functions is not necessarily the whole function, but it's more like just like several lines of code. So they try to find a way to combine all these small pieces of code together, and then forms this so-called the shellcode, right? So we call that, it's more like just combine all these gadgets together and form the shellcode, right? So how exactly this can be done, right? So let me show you first another way of introduce this ROP attack. Another way to introduce this one is actually the ransom note. So remember, this is actually shows you the ransom note. So this return-oriented programming is just like a ransom note, but instead of just cutting all these letters from a magazine, we actually try to cutting out the instructions from all this from this .text segment, which is from the benign software. So this is just like the main idea behind this ROP attack, right? So we are trying to create a ransom note, or not ransom note. We try to just find out all these instructions and then pieces of instructions, and then recombine them together to form a shellcode, right? So that's the idea behind this return-oriented programming. Remember that back when we do this jump to shellcode attack, we try to type in this shellcode by ourselves. This time, we actually try to use the instructions we try to reuse the instructions from the benign software, and then create the shellcode by using the existing this code. Okay. So right, so let's do a quick review before I talk about this return-oriented programming. So we know that this ordinary programming at the machine level is like the program is actually just a stream of instructions, right? So we have an instruction pointer, which is a register called EIP register that inside a CPU. This instruction pointer determines which instruction to fetch and to execute, right? So once this process has executed the instruction, it automatically increments this EIP to the next instruction. And then we know that the control flow, in order to control the flow, we need to change this EIP value, right? So let me show you the one of the examples that we use for class 3, right? So remember that when I showed you the stack frame, we first just deassemble the main function, right? And then inside the main function, we have two functions. One is this add function, right? So let's just deassemble the add function, right? And then inside this add function, at the very last line, right? So this the very last line of this add function is called return, right? So we can just first set up a breakpointer to this to that line of code, and then run the code. Okay. Once I run this code, you can see that this time when we hit the breakpoint, the EIP, this register, which is one of the registers inside the CPU, is actually holding a memory address, which is going to be 0804919B, right? So that means this is going to be the next instruction that are about to be executed. So that means this EIP register is always holding the instructions that are about to be executed, right? Okay, so okay, so now this time the inside is a 0804919B, which is this line, right? It's actually holding an instruction called return, right? So this return instruction is actually one of the unique, very special one, right? This return instructions actually allows us to change the data inside this EIP, right? So what this return will do is that they're gonna first take a look at the topmost data on your stack, which is your stack memory, and then they're gonna put this as whatever the data on the stack memory into EIP. So that means we kind of use this feature to launch our stack overflow attack, right? Because we know that if we can overflow the stack, we can try to alter or modify this value, then we can change the flow of the program, right? So return-oriented programming also use this kind of concept, right? So we know that this is actually the only way that we can control, not necessarily only way, but this is actually the most important method that we can control the flow of the program. It's just like when the program try to code this return, when they code the return, they're gonna take a look at the topmost data on the stack. So if we can somehow like modify this value or placing multiple like values onto the stack, and then we just let the program keep calling this return, then we can just we can just bring this program into anywhere we want. So that's basically the idea of this return-oriented programming attack, and also that's the reason why we call that return-oriented programming, because we are try to use this RET, this return instructions, to combine everything together and then to formulate shellcode. Okay. Anyway, so in case that you forget, let me show you what happens once we hit this return, right? So once you let this program to keep running to run next step, then they're going to put in 0804919C7 into EIP, and then they're gonna brings you to this 0804919C7, right? So let's just run it, right? So you can see that once we pass this, once we execute these return instructions, this time the EIP is actually holding a new value, the value that are on the top of the stack. Used to be the top of the stack, but now the stack is being cleared out, and then the EIP is all actually holding the topmost, the previous topmost value on the stack, right? And then the program is about to run the code inside in this 84917C, this memory address, right? So just quickly review. Okay, so now we know that if we can use this, if we can figure out a way to control control the EIP, which in short just placing the data onto the stack, then we can control the program. We might be able to control the program. Okay. All right. So what is this return-oriented programming? What is the machine level of this type of attack? Right, so in short, what is the main idea behind this ROP attack, return-oriented programming attack, is that we just try to use the original program. Right, so that means we just use this the code section of the program, which we call that .text section. Right, so we just use all these instructions that inside the code of the program, and then we just find out the useful ones. Like say this is going to be several lines of code, 3 lines of code. We call that code 1. And then we first let this program, first we still perform this stack overflow attack. And then we let this program to jump to code 1. And then once they run through code 1, they're going to use code return. Once they return, they're not going to return back to normal. Instead, they're going to return to another piece of the code called code 2. And once they finish code 2, they're going to code return, because as I mentioned, all this piece of code is going to be the one that we find, the attacker find is actually they try to find out all this piece of code that with this RET return at the end. Right, so once they call this a code 2, they're going to execute some command, and then eventually they're going to hit this return instructions, and then they're going to not going to back to normal. Instead, they're going to bring you to code 3. So in short, once we kind of like formulate this chain of code gadget, then eventually, if we're putting everything together, then that will become a very powerful weapon. Right? So this can be considered as our like another way to craft this shell code. Okay. So talking about ROP gadget, right? So this is just a gadget that was created in July 1945. Right? So if you don't know what this is, you can go try to Google it. Right? So this is a very powerful weapon. Right? Okay. So back into this attack process. So some of you guys probably get confused, right? So what the heck is this all this stuff, right? So let me show you a very simple examples, right? Not a real examples, but use this example. You can hopefully that I can use this example to convince you that we can actually launch this type of attack on our computer. Okay. So first you can see that oops, this one does not have a background. Anyway, so first you can see from this picture we have 3 gadgets, right? The gadget G1 is called POP-EX return, right? And we have gadget G2 is called XOR EDX return, and G3 is increase ECX return, right? So the common parts of this G1, G2, and G3 is that they're gonna always all 3 of them are ended with this RET, this return instruction. So that's the reason why we call it return-oriented programming, right? And then here is actually the stack, right? So we first, as you can see, the structure of the stack is quite similar to the one that we learned from previous lectures. We still have a buffer, we have a return address. We have this previous EBP value, but we know that we don't care. And then we have a return address, right? So normally when we perform this return hijacking attack, we're simply just changing this return address to hacked function, right? So we're first just changing this one to hacked function. So they're gonna just calling this hacked function, and then boom, that we just finished the job, right? So normally that print out hacked by someone, right? So we know that. But this time we change it. We change it to something like this. We change it to the memory address of this gadget 1. So that means once we launch this attack, once we launch this stack overflow attack, they are going to jump to gadget 1 because we changed the return address to gadget 1. Okay. So, but that's not it. Instead, with this time, our payload is actually much more complicated. It's a little bit complicated than before, because previously we're just using dummy characters plus return address. But this time, after the first return address, which is the gadget 1's memory address, we added another actually 4-byte of value, 41, 42, 43, 44, which means the ABCD, right, in upper cases, right? So we just adding this ABCD, this 4 characters, placed right after this memory address of gadget 1. And then after that, we're placing another memory address. So that means our shell code, or sorry, our attacking script, right? This payload is actually has 3 memory address. So this is actually memory address of gadget 1, and then followed by ABCD, followed by another memory address for gadget 2, followed by another memory address of gadget 3. Okay. All right. So if this is the structure that we put, if this is the payload that we put it there, then let's take a look at what's going to happen, right? So first, at the beginning, we know that of course they're going to use this gadget 1 to jump to this piece of the code. So this piece of the code is called POP-EAX. So what is a POP-EAX means? That means they're gonna pop out the topmost data from the stack, out of the stack, and then put into EAX, right? So what is the topmost data? Because we know that once you trigger this trigger this stack overflow attack, this gadget 1, because it brings you to this gadget 1, then that means this memory address is actually being popped out. So once it's popped out, then we know that by the time when you run this POP-EAX, the topmost data on the stack is actually this 41, 42, 43, 44. So that means we're actually putting this one into EAX, which in short means that we're putting this A, B, C, D, those 4 characters into EAX, right? And then once we've done that, this value is also being popped out and then put into EAX. And then after that, the next instruction is called return. So we'll try to call return. Once you call return, then basically the same thing gonna happen. They're going to pop out the topmost data from the stack and then putting this one into EIP register, and then the program will jump to that memory address, which in our case, they're going to jump to here, jump to this memory address. And once they jump to this memory address, they're going to do this XOR EDX, which simply just setting EDX to 0, right? So we know that XOR the same value with the same value, then they simply just return 0. So it's more like clear out this EDX to 0. And then we're going to call return again. So once they call return, we know that this time they're going to use the topmost data on the stack, which is actually the memory address of the gadget 3's memory address. So they're gonna bring you to here to G3, and then they're gonna increase this ECX value by 1 and then return it back. Right. So as you can see that the real execution of this of the code, if I'm placing all this stuff, let me just use this as a reason, wipe it out. So if I'm placing all this stuff, right, all this stuff onto as the payload, as the attacking payload, the real execution is actually this. First, putting this ABCD into EX, then clear out EDX, setting EDX to value 0, and then increase ECX value by 1. So as you can see, that's just like the meaning of the code, and then we can actually control it by putting the memory address of gadget 1, gadget 2, and gadget 3 onto the stack. And also we can also put our own values. But if we want to set some values into putting some values into any registers, we can also find the corresponding gadget, and then by placing the value onto the stack, we can also put in any values we want. And why this tag works? Because as you can see, we're not violating the rules. Again, this time we're not trying to jump to this part, because we previously, when we call this jump to shellcode attack, we are trying to jump to this buffer, right? So we understand this buffer, all this memory is non-executable, so it's fine. We're not putting our shellcode in here. Instead, this piece of memory cannot be marked as non-executable, because this is supposed to be executed. This is actually the program itself, right? So this piece of memory belongs to the program itself. So all I have to do is just try to create a link to executing piece of the memory, piece of the instructions inside the executable memory, and then we somehow control it and then formulate the shellcode. Right. So that's the main idea behind the return-oriented or ROP, this attack. Right. If you still get confused, don't worry about it. I'm going to show you like 2 examples to show you how this attacks, how this works, why this is gonna work, right? But before that, let me first tell you the several things that we need to know. First is how to find this gadget, right? So this G1, G2, G3, right? So we call that the gadget. So how to find the gadget? There is actually several ways to find the gadget. There's first is actually the old school method is to use this obg dump, right? Obg dump, this command actually shows you that once before when we talk about the shell code, right? So if you forget, you can go back and check the video for when I teach this shell code, that section, the system code and shell code. I think it's class 3 or class 4, right? So you can go back and check. And then using this script, right? So in combine of these 2 instructions, you can find out the gadget. But the some gadget will not be found because this obg dump aligns instructions, so sometimes you might not be able to find all this gadget. Of course, another more advanced way is just try to make your own tools, right? So some of you guys probably just for lab 1, you probably just talk to me that there might be some other ways to find out to generate this this debridging sequence, the cyclic string, right? Of course, there's just multiple ways. A lot of tools can do that. So my suggestion is that you can just pick up the one that you feel you're comfortable with, and you can just use it, right? And well, but that just use other people's tools. A better way is just try if you can make your own tools because you know how to program. Then if you can program your own tools, then that will be like your own asset, so you can just use that to any different situations. Of course, at current level, we can just use existing tools because most of the time we don't want to spend too much time on how to on all these very details about how to find the gadget, right? So there's might be a lot of like tricky things. So using an existing tool is good enough. But this just does not answer the question how we can find the gadget, because there's several things. We still need to know what is the property of a gadget. So we just need to find out this. Give a program. We actually first need to write a program to take a look at this code section. So that means we need to first deassemble like the main function, right? So you can see that this is the instruction of the main functions, and then inside this main function, we need to find out any instructions that is ended with return. So for example, this could be a gadget, right? So like say this move, leave, return, this could be a gadget, can be considered as a gadget, right? Or add function. Inside this add function, you can see that the very last sentence also called return. Right? So we can also use this return, this RET return as a gadget, right? So any instruction sequence that ending in return is potentially useful, could be part of the gadget, right? Right. So to find this ROP, the gadget for ROP, there's actually a very useful tool is called ROP gadget, right? So we can use this program to help us to find out all this gadget in a binary program. Okay. So once you log in, so first you can just log into this Badger CTF. So once you log in, you can just try to use this. This tool is already been installed, so you can just type this ROP gadget, right? So this ROP gadget and this ROP PR, both can be used to find this ROP gadget, right? So this is actually 2 quite useful tools that you can use. So let me just show you the first one, this ROP gadget one. Right? So we can just type ROP, just like this one. We can type ROP gadget -- binary, and then followed by the program's name, right? The program that you want to analysis. So it just happened that inside my this directory, there's a program called lab2. I'm going to delete it probably, but but just use this as an example. You can use to apply this instructions to any binary program. So we have this lab 2, so let's just run this with lab 2. So you can see that once I type lab 2, hit enter key, you can see that they're gonna print out all the gadget that we can use. So most of the gadget is actually ended with return, but some gadget is actually ended with this call function, right? And some is ended with this jump function, right? So this is actually all the gadget that can be used and be defined by this program. Okay, so now we know how to find this gadget. The problem is the next question is how to like formulate the shellcode, right? How to formulate the payload, right? So how to create the shellcode by using by placing gadget together. So before I shows you the final solution, let me just first show you a program, an example program. And this program is very similar to the lab 3 that you are going to do, right? So please pay attention to this program because I'm going to use this like toy example to show you the main idea behind this ROP. And also this ROP, this concept is quite important because in all the rest of the lectures in this semester, we're going to apply this concept over and over again. So please pay attention to the next few slides. Okay. All right. So first, let's take a look at this the program. Okay. So this program has 5 functions in total. We have this execute string, add bin, add bash, and vulnerable function, and the main function. Right. So the main function will first calling this vulnerable function. Inside this vulnerable function, you can see that they are using this gets function, which will take user input. We know that gets function is dangerous because they don't check the boundaries. So of course there will be a buffer overflow vulnerability that has been like introduced by this function. Okay, so we know that we can basically trigger this buffer overflow. Once we identify this vulnerability, then we know that we can control the program. We have one-time chance to control the program. So that means we can override the return address and then letting this program to jump to any functions that we want, right? So that means we can actually letting them to jump to either execute string, add bin, or add bash function, right? So or jump to main function. So we can let it jump to anywhere we want, but only like one time, right? So as you can see, this time is a little bit different than compared to the first example, this return hijacking attack, because we need to jump to all 3 of the functions to launch a successful hack. Because you can see that at the top we have a string char type buffer called string, right? And eventually this execute string function will execute whatever the string that have been put inside this array. So that means they are going to execute it by calling this system function. System function is equivalent to typing the command inside the command line shell. All right, so what is the command we want to execute? We actually want to execute a command called -bin /bin /bin/bash, right? So we want to execute this command. So we want to putting this one into the string. So if we can putting this string into this string array, then calling execute string these functions, then we know that this command will be executed, right? And once this command will be executed, then we will be able to get our shell, because if you are typing this command inside your inside any shells, like say bin bash, then they're gonna provide you a shell, right? So you can see that this time the color is actually changed because they actually give us a new shell. So we want to execute this command, but this command, in order to execute it, we need to call system function, and then we need to placing this string to the string array. Luckily, you can see that there's actually 2 functions to help us to do this task. So this string cat function is basically just means moving this bash into string, right? And then string cat, the first string cat is actually moving this bin into string. So we know that if you're calling this bin function, add bin functions, they're going to add the first part of this command, they are going to add the bin part into this string array. And if you're calling this add bash, they're going to add this bash part to this string array. So the execution plan is like this. So if we can first trigger this buffer flow vulnerability inside this vulnerable function, and then let it call this add bin function, they're going to add this bin, this backslash bin into string. Then we want to call add bash function, which allows this system will add this backslash bash onto slash bash into this string array. And then once you're calling this execute string, they're going to run this command, which will give us a shell, spawn a shell, right? So that's the plan, right? So if this is the plan, then so it seems that's the plan. But the question is, we only have like one chance. Like say, if we use this return hijacking attack, we can only trigger just buffer flow once, and once it triggered, it can bring us to this add bin function for sure. But then after that, we cannot jump to, there's no way, or at least based on if we're not using this ROP, if we simply return hijack, then there's no way to go to this add bash, and there's no way to go to this execute string function, because once they finish this, once we choose this add bin function, then that's it, right? So we're gonna stack into this add bin. Once they finish, then the program will be back to will finish, right? So that's a problem. Okay. All right. So now we actually I'm going to actually show you how to like achieve this goal, how to formulate this the payload, and then eventually make sure that we can follow this execution path that have been written here. Okay. All right. So how to do that? Before I show you that, there's actually another two things we need to take into consideration, right? The first thing is that when you call this add bin function, they actually have an if structure. They're gonna check the past argument magic, right? And if the magic is equal to dead beef, 0x dead beef, then they're going to execute this command. So that means when you're calling this add bin function, you cannot simply just use the return hijack attack and then jump to here. Instead, you not only need to you need to jump both. I mean, you need to first jump to here, and also you need to successfully pass a integer, and this integer's value must be equal to 0x dead beef. Otherwise, this string concatenation, this function will not execute. Same thing for this add bash. This one is actually much more complicated, because you need to passing two arguments, and then the first argument's value should be equal to cafe baby, and then the second should be equal to this bad food, right? So 0x0 bad f00d, right? So if this two arguments value is not equal to this value, then that will be a problem. Okay. So that means this execution path is actually means that we need to first figure out a way to call add bin, but at the same time also passing a variable called magic, and then the value should be equal to dead beef. And then we also need to calling add bash after calling add bin, and then passing another two argument, then calling execute string, and then eventually we got the shell. Right. Okay. So alright. So because we want to passing argument, so how to do that, right? So how to parse argument to a function. Remember that in the previous lectures, right? When I teach you this stack frame, this part actually shows you how to pass argument. Remember that this is like the stack layout, right? So we know that the stack, every time you create this new stack frame, that means you're calling a new function, right? So and then there's an ESP and EBP value. One thing that I mentioned is that every time you're trying to passing some argument to a new function, you need to first just place them onto the stack, right? And then on top of that is actually the return value. This the old EIP value. So this is actually a new stack frame. So this is the stack frame for this full function, right? So this is the stack frame belongs to this full function, and this part is actually how you're passing this argument 1, 2, 3. So this ABC here is actually just 1, 2, 3, right? Which is the argument that you passed here. So in short, we actually use this stack for helping us to pass argument. But this time, instead of putting ABC on the stack, we need to put in the actual value 0x_beef on the stack. So if we can find out this if we can formulate, if we can first we can trigger a buffer overflow attack, and then once we trigger this buffer overflow attack, we can try to create some stack looking like this, right? So let's say if I simply just want to pass in one argument, right? In this example, passing 3 arguments. Simply, if I just want to pass in one argument, which is this 0x_beef, then the structure should look like this. First, we're going to use we're going to have this old EIP, which is the return address, which is actually we're going to put in a new address here, and then right below this return address is actually the argument. So this is the argument that we want to pass, right? So what that means? That means that if we can consider like this. So this return chaining is like this. We need to have a return address, and then down below this return address we have the arguments value. So that's basically the idea of how to passing an argument to a function. Okay. All right. So before that, so now let's go back and then take a look at this execution path, right? So this time we want to first figure out the structure of the payload. So the first thing we need to do is, of course, first we need to trigger this buffer overflow, and then we want to call in this add_bin function. And then once we finish add_bin function, we can call in add_bash, and then eventually calling this execute string. So we want to call in 3 functions. So in short, this is actually the return chaining, right? So of course, this is definitely not gonna work, right? So this is not the final version, but at least I kind of shows you the idea, right? So without any parameters, we want to make sure that our ROP chain should look like this. If we can have this, first we need to have some dummy characters A's, or just try to make sure that we can overflow the address. So I mean, this is actually our payload, right? Similar to the lab 1, right? So our payload for lab 1 is simply just dummy characters plus the return address. But this time we want to jump to 3 functions. So in this case, we want to make sure that we have a dummy characters, which of course we need to find out the length of this dummy characters, the magic number, right? So once we find out, then we want to place the address for add_bin function. If you can place the memory address of add_bin function, they are going to run through all these instructions in add_bin function, and eventually they're going to hit the very last instructions inside the add_bin function, which is definitely going to be return. Once they hit return, they're going to actually take out the topmost data, which in our case is going to be the address of the add_bash function. So they are going to jump to add_bash function. And once they finish add_bash function, then they are going to take a look at the topmost data on the stack, which is going to be the address of the execute string function. So that means if the payload is look like this, dummy character A is followed by address of add_bin, address of add_bash, address for execute string, then this is going to work, right? So that's the return chaining without parameters, right? So by placing 3 memory address onto the stack, and then layer them, putting them like in this sequence, and we can make sure that each time when they call return, they're going to return to, it's guaranteed that they can return to another function. So we will actually try to interleaving the 3 functions together, right? So interleaving 3 functions together to formulate code. The question is, but the problem is that we actually need to pass in parameters, because when you're calling this add_bin function, you need to pass in argument, which is name is magic, and then the value should be equal to 0x_beef. So this time we need to recall the structure like this. So we need to place in the argument right below the return address, and then so we need to first have the function address, which is the function we want to jump to, and then once you jump to, then we need to have a return address, which is the next function we're about to call, and then down below this return address, we need to put in the arguments. Translate this one into our payload. It should be look like this. Right? So this part can be a little bit confusing. So let me spend some time to talk about this. So for this addBin function, we need to pass a value called 0x_deadbeef. It's a hexadecimal number, right? And then that means when you call this addBin function, we need to pass in an argument to this function. But this argument, in order to passing argument to a function, we know that we need to follow this structure that we learned in this stack frame class, right? We need to follow this kind of structure. So what structure? The structure is like this, right? So this slides, this page 24 is quite important. So please take a look at this. So we need to first put in this function address of the function that the function you want to jump to, which is the return address, right? So that means this is actually allows us to first, this is the dummy characters, right? And then this is where the function you want to jump to. Once you jump to, then this part will be removed from the stack. So the stack will looks like this. They're gonna have a return address, which is the next function you want to jump, and then down below there should be the arguments. Okay. So in our case, we need to placing them like in this way. Right? So first, we need to have some dummy character A's to trigger this buffer flow. So the program will jump to this addBin function. And we know that once you jump to the addBin function, this address will be popped out. Of course, the dummy character and this stuff will no longer exist. So that means inside addBin function, if once you program runs into this addBin function, right? If this Stack Overflow attack, you successfully launch this type of tag, then inside this addBin function, if you take a look at the stack, the topmost data of the stack is actually the address for addBash, right? So it's actually this addBash function's memory address. And then follow this structure, right? So this addBash function is considered as the old EIP value. So that means down below this old EIP is where we need to put in this argument. So that means the 0x_deadbeef is actually need to be placed under this two memory address. So this part can be confusing, and I know that, right? So sometimes students just don't get it why we need to put in this one under this addBash function. That is because this memory address of the addBin function is already popped out. Once you are inside this addBin function, this address of the addBin function is no longer on the stack. Instead, the topmost data is actually the addBash function. So that means if we still follow the structures, then the argument should be placed under this return address, because on top of this addBash function is supposed to be the new stack frame. This is supposed to be the new stack frame, which this part, the old value, the address for addBin and the dummy characters is no longer exist. So this part is considered, all this free space is considered as the stack frame for the addBin function, so you can freely use that. And then this is supposed to be the return address. The address of the addBash is supposed to be the return address of the addBin function. So the argument of the addBin function, it should be placed under this address of addBash function, which in our case should be 0x_deadbeef. So that's how we place this. This is where we place this argument. So please just take some time to spend some time to think about this, and then try your best to fully understand why we need to placing it down below here. Right. So once you know that, then the logic of the program will be much more clear. So that means first, if we write in this way, then we can successfully do two things. First, we will be able to call this addBin function, and then at the same time we can pass in this argument as 0x equal to 0x_deadbeef. And then once we finish that, it's also guaranteed that we can jump to the addBash function. But that's it, right? So once you jump to the addBash function, then there's a broken link. First, there's we didn't pass the other two arguments for addBash function, and also there's no way that we can jump to this execute string function. So there's actually a broken link here. So we want to fix this broken link, right? So how to fix this broken link, right? So before I jump to the idea, let me just first show you why there's a broken link, right? Why I say that there's a broken link, because as I mentioned, if there's no parameters needed, then all I have to do in order to interleaving the three functions, to calling three functions, then we're simply just placing all this memory address of them onto the stack, right? But now we need to pass in arguments, so therefore after several analysis and then several things I teach, I said that we need to simply just put in this argument under this add bash, the memory address of add bash. But why I say that if I do that, there will be introduced a broken link is because this time you can consider that if there's a once we're calling add bin function, once we finish add bin function, they are going to jump to add bash function, right? And once we finish add bash function, they are going to jump to 0x-deadbeef. 0x-deadbeef is not a function, so therefore they are not. You can now jump to you can no longer jump to this execute string function. So that's the reason why I said there is actually a broken link, because that 0x-deadbeef is an argument, but if you somehow placing this argument onto the stack, then eventually once you finish this add bash function, they are going to jump to this memory address. So that's not what we want. So therefore we actually introduce a broken link. So that means every time you introduce parameters, every time you introduce an argument, right? So you want to pass in this argument to add bin. So this will allow you to pass in this argument to add bin, but at the same time, it also will place a hurdle because you will no longer be able to jump to this execute string function. So is there a way to solve this? Well, this is the time that we actually need to use a gadget. Right, so we need to use the ROP gadget to help us to solve this problem. How to solve this problem? If we can find a gadget to allows us to clear out this deadbeef, 0x-deadbeef from the stack, then we can continue this link. Right? So how to do that? So the solution is very simple. We use a pop return gadget to push the argument 0x-deadbeef into a register to remove it from the stack. Remember that this pop will pop whatever the topmost data from the stack and then putting into some registers or putting some memory addresses. But we don't care because once normally it's registers, right? So we don't care because we simply just use this pop to clear to clean things, right? All right, so let's take a look at this new version of our shell code, right? So now the shell and the payload. So the payload is actually become a little bit complicated. First, we have dummy character A's to make sure that we can successfully trigger the buffer flow. Of course, the magic number still we still need to find this magic number, followed by the address of the add bin, and then instead of followed by this address of add bash, this time down below here is actually putting an address for a pop return gadget. So this gadget only have two instructions. The first instructions is pop something, pop EX, right? Or pop EBX. We don't care, but there should be a pop instruction. And then the second instruction is return, right? So because the return will allow us to make sure that we can still return it back. And then after that is actually 0x-deadbeef, the argument we want to pass to add bin function, and then followed by this address of this add bash function, right? So why this is gonna work, right? Let me show you why this is gonna work. First, if you create this payload in this way, first this dummy character A's will trigger buffer overflow, so that will brings us to this add bin function. Once you're in the add bin function, right? So this address will be removed. So they will think that this is going to be the return address, and this is going to be the argument you want to pass. So therefore, the computer will passing this one to add bin function, which will make sure that this magic will equal 0x-deadbeef. So the add bin function will be executed successfully, and once finished, they're going to return back to. They're going to use this. They're going to jump to this gadget. This gadget is only have two instructions. The first is pop. So this pop instruction, once you inside the gadget, this all this address will be deleted, right? So once you inside this gadget, they are going to first do this pop. Once they do this pop operation, this 0x deadbeef is actually going to be popped into some registers, right? So that means 0x deadbeef will be removed. Then this gadget will be followed by a return instructions. So this return instructions will basically take a look at the topmost data. Well, in this case, the topmost data will become add bash, right? The address for add bash, and then they're gonna putting this memory address into EIP, right? So therefore, we'll be able to go to add bash function, right? So that means if we formulate the payload in this way, we can do a lot of things, right? So first, we can go to the add-bin function, and we can pass the argument. And once we finish, we can also clear out this argument, and we can also go to the add bash functions. So hopefully that you can understand. If you get confused, just try to think this by yourself, right? To think that you just try to imagine that your head is your computer stack, right? How to process this payload, right? So you will eventually know this, right? Anyway, so this is just how the first part, and then we know that these things we still need to do the same trick for this add bash function. So for the add bash function, we do the same trick, but this time we're just adding several picking up a different gadget, right? So followed by this address of add bash, right? So that means first we know that we eventually can from the previous ones we can successfully go to this add bash function. Once we're inside the add bash function, then this cafe baby and bad food will be considered as an argument that will be passing into this add bash function, and in this sequence, right? So the top one will be treated as a magic 1, the second one will be treated as a bad food, 0 bad food, right? So therefore we can successfully calling this string concatenation functions. And once finish, then they are going to use this they're going to jump to a gadget. This gadget is called pop return. So the first pop will be, because when you're inside this pop return, we know that the topmost data, once you are inside the gadget, the topmost data is going to be cafe baby. So the cafe baby will be first popped out, and then the next pop will allow us to pop out this bad food. So that means these two arguments, by using this pop return gadget, we successfully clear out this cafe baby and bad food. And then once they do this return, we can actually placing this execute string, the memory address of the execute string below. So they're going to return to this execute string. So therefore we can successfully launch the command and then get the shell, right? So in short, this is actually the final payload structure, right? It's a little bit complicated, right? So first we have dummy characters to make sure we can trigger buffer overflow, and then jump to add-bin function. And then once we're in the add-bin function, deadbeef will be passed. And once we've passed deadbeef, finish add-bin function, pop return will be called, so this deadbeef will be removed, and they are going to return to this add bash function. Once we're in the add bash function, this two cafe baby bad food will be passed as an argument. And once we finish add bash function, we're going to go to pop return. The first pop will clear out cafe baby, second pop will clear out the bad food, and once you call return, they're going to jump to the execute string, right? So that's the idea, right? Hopefully that you can also try to imagine this whole procedure by yourself in your head, right? So that's the final version of the payload. All right, so now I shows you how to create this, what is the structure of the payload look like. Now is the time to actually write the code, right, to launch this attack. All right, so first the program will be, I'm going to place this class examples, and then inside this class 6 inside the folder class 6 examples. And of course you can also try this by download the source code from our class website. So the source code is called ROP.c. You can take a look at this ROP.c, which is shows you the exactly same code as the one that shows in the slides, right? So that's the code, right? That's the program we want to attack. So first, of course, the first thing we need to do is simply just compile this program, right? So in order to compile this program, we need to type gcc-n32 to convert it to compile this one into 32-bit mode, and -f no stack protector, right? -no f no stack protector, and then normally we also before in the previous lecture I said that we need to do the -zexec stack, right? So to turn on this DEP, but this time because we are launching this return ROP attack, return oriented programming attack, so we don't need to adding this flag, right? So we don't need to add this one because we are not using this jump to shellcode attack, right? So in this case we can turn on this one, and then after that we can just also we can add this -no PIE to make sure that to turn off this position independent environment, right? To make this program more easy to read, and then we can just write this -o output this code ROP, right? So sorry, at the front we need to write gcc ROP.c. So this is the source code we want to compile, and then this is the output binary format. Right? So once you hit enter key, they're gonna print out some warning information. We know that basically tells us guess function is it should not be used, but anyway. So okay, so that's a program. So we have this ROP, this is a binary program, right? So it just compile and generate this binary program. Now is the first thing we need to do is, of course, we need to start writing the Python script. Alright, so for the Python script, we can first just borrow the attack.py, the one that we use for our first attack, that's the return hijacking attack, right? So we can simply just borrow this one. But we need to make, of course, this is not for this ROP program, so we need to make a few adjustments. So first, let me just edit this attack.py, right? So first, the first thing we need to change is the process name, right? Some students just keep asking me question why every time they run the code, they shows the error information, because you need to make sure that this the binary program exists inside your directory, right? So in our case, we need to make sure that this Python program should call this ROP, right? ROP is actually the program we just compile and then generate it. This is the ROP, this is the binary program, okay? And then the return address is another thing we need to figure out, right? So the return address based on our slides is it's going to be the address of this add-bin function. This is actually the return address, right? And then also we need to figure out this the length of the dummy character is, right? So we also need to figure that out, okay? So okay, so first we need to call this gdb ROP, use this gdb to run this one, and then after that we need to first what do we need to do first is to first we need to deassemble this add-bin function. So we need to first figure out the memory address of the add-bin function, which in this case is going to be the 0x080491AD. So that's going to be the return address, right? Okay. So first we just putting this one. So this time we can change this return address to another version. So we can just rename it to this add bin, right? So this is actually the memory address of add bin function, and the payload will be changed. So instead of using this old payload, we can just changing this payload to a times 42 plus 2 this add bin, right? So that means this is actually the first part, the first two of this payload. But this magic number is definitely incorrect, right? So this time we're not using this 42, we need to use a new number, right? So we need to figure out how to find out this magic number. Basically, we can use the same technique that we use from our previous lectures, right? Remember that in order to find this magic number, we need to first just run this GDB and then call this pattern and then create and then passing a number, right? So for this program, right, this ROP.c, this program, the buffer is actually equal to 100. The size of the buffer is 100. So that means we probably the magic number probably is definitely going to be larger than 100. So we need to create 150 should be enough, right? Should be good enough. Or you can create 200, right? So first we just create this string, right? So this is going to be the string, and then we can save this one into a files, right? So there's a better way to do that, but anyway, so we can just create this just call that string, and then just putting it into this files, and then we can go back to GDB and then rerun this program. This time we can run this program by feeding this string into this program, right? So run this program and then putting string in it, and then once you're putting it, then this time the program will stop, and then we can just do this pattern search and then type this EIP. So this time they actually tells me that the offset is actually 112. So we know that this time the magic number is actually 112. So we can change this one to like this. That means characters plus, instead of 42, this is will become 112. Right. All right. So this will be the first part of the shellcode. The bit is actually the one that we use in our previous lectures, right? So, but we know that this is not the end, because the full structure of the shellcode should be like this, right? So we need to keep adding like new steps in it, right? Okay. So we know that the shellcode should be like this. First, we need to use this the payload should be like, first we have this dummy characters, and then we have this add-in function, and then after that we need to have an address of this pop return gadget. So how to find this pop return gadget? As I just mentioned, we can use this ROP gadget to help us to find this gadget, right? So let me show you that. So right. So we can just type ROP gadget, and then dash binary, and then followed by this ROP. Right? So they're going to print out all the gadget that is available that we can use, right? So the gadget we want to pick is called the pop return gadget. So we just need to find out any gadget that start with a pop and then ended with a return. So you can see that there is actually one gadget that fit for actually two, actually this one, right? Pop EBP return. This can be, we can use this one, or if you want, you can use this pop EBX return, right? So both are considered pop return, but the only difference is that the first one, pop EBP, is popping the data into EBP register. This is actually putting the data into EBX register. But we know that it really doesn't matter which registers we use, right? So let's say that I just use the first one, this pop EBP return, right? Okay, because we just want to discard the data, or just want to clear the stack, right? We don't care which register's been holding this data. Right, so now we can simply just, if you want to use this gadget, we simply just need to copy this memory address 0x0804931B. Right, so we can just copy and then putting this one into here. So this time this is called pop return gadget, and the memory address will be this one, and you can delete this one. Right. So now we have this pop return gadget, right? And then the payload will be just like a payload plus equal to pop return. Right. So you need to add in this pop return at the end. It should be P32, right? So we also need to convert P32 pop return, right? To convert this one from this format into little endian format, right? So anyway, so that's just adding this to the payload. All right, so let's take a look at the payload. So the next one is going to be 0x dead beef, right? So we want to adding this one to our code, right? So it's going to be payload is equal to plus equal to p32 0x dead b. Okay, and then after that is actually the address of the add bash function, right? So the address of the add bash function, we still need to do use this GDB to find it, right? So we need to use GDB ROP and then deassemble this add bash, right? And then the first memory address, which is going to be 0x080491F4, is going to be the memory address of the add bash function. Okay, so we're just adding it to here, right? So you can add it to the top, right? So add bash is equal to 0x. This is going to be the memory address of add bash, right? And then we just simply just adding this one to our payload, right? So this is going to be add bash. Okay, and then followed by this address of this pop-up return gadget. So we need to find this memory address of this pop-up return gadget. Okay, so if you recall that there is actually this is actually the pop-up return gadget, right? So we can definitely use this one, pop edi pop evp return, right? So this is the pop-up return gadget. So the memory address is going to be 08049318. Okay. So we're just adding it to here. Pop return is equal to this one, and then we just add it to our payload. Payload is equal to pop return, right? Okay, so now we have this almost done, and then there's just one and then two argument, cafe baby bad food, and the address of execute string. So let me just finish all of them. So first we need to just copy this one to here, and then copy two lines, and the first one is going to be cafe baby, not BABY, cafe baby, and then this is going to be 0 bad food, right? So that's going to be 0x bad food, and then followed by the memory address of the exec string, right? So this is going to be the memory address of the execute string. So still need to code this GDB and then run the code and deassemble the execute string function. Right, so this execute string function's memory address is here, right? 0x049182. So we can just putting this one into a text.py. Okay. Right, so right here. Okay. Right, so that's going to be the very last one. Just delete it. Right, so that's the full payload. So you can see that this time is actually a little bit more complicated than the before, right? So first we need to figure out the magic number, and then demi characters plus times the magic number, a lot of A's, followed by the first memory address add bin, and then followed by return pop return gadget, and then our first argument, and then add bash the function memory address of add bash function, pop return the memory address of this pop-up return gadget, and then two argument, cafe baby bad food, and then memory address of the execute string, right? So that's how but luckily we just managed to find all of them. Okay, so once we find out all of them, then this is time that we can actually launch this attack. So this is actually the moment of truth. So if everything went correctly, we should be able to launch a shell. As you can see that I can actually type command, right? So they're gonna tell me this is actually means that we successfully launched this attack. So, and that's the end of this example. Okay. All right, so the second example is called ROP.c, right? So this is also a program, right? So we have this main function, and also there's another function called a vulnerable function, right? So this vulnerable function create a buffer and then try to read the user input by using this read function, right? again, this read function is supposed to be dangerous, so therefore there's no like they don't check the boundary, so therefore we can actually how to say, we can actually launch this buffer flow attack. But again, the question is like, once we can launch this buffer flow attack, because we know that this DEP is being enabled, so we can now write our own shell, right? So we can just assume this DEP is enabled, so we can now like use this jump to shellcode attack. So how to run this return-oriented programming attack for this program, right? So how to craft the shellcode, because this is actually the real-world program. It's not like the toy program that we use for the previous example, right? So this is actually a program that does not have this add bin add dash execute string. So can we still attack it, right? All right, so let me show you how to do that. So first, let me just compile. I already downloaded this ROP2.c from our website. So let's just compile this. So same thing. First, we want to compile this ROP2.c with the M32 flag, and then adding another flag F, no stack protector, right? And then no PIE, and then -o want to output the binary name is called ROP2, right? So compile this, right? So once you compile, then this time there's no error information, but anyway, so we know that's the code, right? So the problem is how to like launch this ROP attack and then get a shell, right? Because we know that this ROP2, this program contains this buffer flow vulnerability. Right? Oh, not this one. Right, so it contains this part, right? So this is a string copy, and then this read function is actually contains this buffer flow vulnerability. So we can definitely try to attack it. So the idea of attacking this ROP2 is this example is to use this Linux system calls, right? Remember that in the previous lectures, I tells you that every time when we try to launch a shell, we need to use this concept of so-called the system call, right? So the system call, as I mentioned, is basically allows you to temporarily elevate you from ring 3, brings you from ring 3 to ring 0, so you will temporarily become the root user. And then the system call, every time you want to do that inside Linux, you need to do this interrupt 0x80, right? So there's a lot of different type of system calls. This is actually a table shows all the system calls we can use. And then of course, in order to get a shell, in order to run some command, the system code that we want to use is actually the one that allows us to execute a command, which is this 11, right? So the system execv is actually allows us to execute a command. So you can follow a command, but you can also putting this command inside this EBX register, right? So that's actually the memory address that pointing to a string that this string will be executed. So that's our plan. So that means we can use this number 11, this system execv. This system call is equivalent to we can invoke this function and then to call this execute command, and then we're passing the command bin sh with with 2 zeros. Right? So how to launch this system call? As I mentioned in our previous lectures, if you forget, you can recall, you can check the previous lectures. But like quick review. So so if you so this is gonna be if we take a look at the system call reference, then we know that we simply just need to prepare the value into putting the corresponding values into EX, EBX, ECX, and EDX. So in this case, if you read it, this EX value should be equal to 0x0b. EBX should be putting a string that a chart type pointer pointing to the command, and then EDX and EBX, ACX and EDX should be all setting to 0. So this is actually both should be set to 0. And then EX should be equal to 0xb, EBX should be equal to bin sh, should be pointing to a memory address that is holding this bin sh, this command. So that means if we can find a way to set this register EX, EBX, ECX, EDX in this value, then we can, and then also we can find out this interrupt 0x80, and if we can please putting all these pieces of steps together, then we can get a shell. So therefore, this is actually how we create the shell code, but also this is actually how we can use how we use this return-oriented programming attack to attack this program. So we need to find out the gadget allows us to set EX to 0xb, EBX into this pointing to string, and also we need to find a gadget that allows us to do this interrupt 0x80 to launch system call. Okay. All right. So of course, one way to do that is just like use this ROP gadget, right? And then do this dash binary, and then try to analysis this to try to find out all this gadget that inside this ROP2, and then we can just putting all of this gadget together, right, by ourselves. But the problem is this is very time consuming, right? So there's actually automatic tools that are available that inside this ROP gadget. If you type this ROP gadget -- help, they're gonna print out all the available options argument that you can use. One of the argument that I'm going to show you is called this ROP chain, which will enable the ROP chain generation. So if you type this ROP chain -- ROP chain, they're going to generate this ROP chain for you. So you don't have to like try to piece everything together, right? So that's great, right? So this is actually a lot better. So therefore we can just try this, right? So we can just type ROP gadget -- binary and the ROP2, right, to first analysis this binary program, and then tap -- ROP chain, right? So if you run this, you can see that they actually first print out all this ROP gadget, and then they try to do this ROP chain generation. But the problem is actually we got the error information because they cannot find this move dword pointer R32 to R32 gadget. This is because the gadget that we found is actually 191, which is not like, I mean the gadget library is just not big enough, right? So they cannot find the appropriate, enough gadget or the right gadget to formulate this ROP chain, right? So that means if this is the program that we use, then if this is the ROP2, this program, like that's the binary program looks like, then we cannot like attack it, right? So because this ROP, theoretically we can do this, right? We can just putting everything into EX, EBX, ECX, EDX, interrupt 0x80 to get a shell. But the reality is that the code base is just too small. The code base is too small, so we cannot find enough like gadget. Right. All right, so that's unfortunately we cannot attack ROP2 this program like in this way. Of course, if there's no way to attack, then I will not putting these examples here. So actually, there's one way to allow us to hack it. It's called we can use this so-called we can just try to compile this program as a static linked ELF program. So what is a static linked ELF means? It means that you can see that this ROP2.c, this program, include a lot of libraries, right? So they include all these libraries. Normally, when you try to include this library, they actually use a so-called dynamic linking, which I'm going to show you what is the difference between these two in the next lectures. But you see that this normally they're just not going to include it, but instead it just refers to some of the other like files. But if you try to compile this one statically, and then create a static link ELF, then all the code inside these libraries will be like put into this final binaries. So that means the final binary files will be a lot bigger than our current files, and therefore all the code that inside these libraries will also eventually become part of our binaries code, which is great because in this case we may be able to have enough gadget, right? So how to compile this one? As how to statically link, create a statically linked ELF is just add this flag -static, right, when you compile these files. So let's just retry this one. So this time when I compile these files, we just rerun this program. Let me just clear it, right? So this time we call that GCC ROP2.c dash static and dash M32 dash F no stack protector and dash no PIE dash O ROP2. So this time we're actually just adding an extra flag. Okay. Alright, so after generate this ROP2, then this time we can try to run this ROP gadget command and take a look like how many gadgets that we have after we finished, well, after we done this static linking. So you can see that this is actually a quite different result, right? So this time we actually have a lot of like gadget which is available. So this time I think we might have enough gadget, right? So it's still printing, right? So let's take a look at how many gadgets that we have at the end. Okay, so you can see that the unique gadget that they find is actually 39,000, which is, I think, is good enough. So this time we're just adding this ROP chain at the end. So the whole command is like ROP gadget dash dash binary ROP2 dash dash ROP chain. Let me just clear it out so and put it up front, right? Dash the ROP chain. So this time it's not only going to print out all this gadget again, but at the end it's also going to show you how to compose this ROP chain, right? Like using Python. Just wait a second, wait a moment, because it's actually, I mean, wait a few seconds because I still keep printing. Once they finish printing out all this gadget, this unique gadget, then they're gonna start to like shows you all the steps, right? So they actually find this write where gadget, and then initial system call number gadget, initial system call argument gadget, and then eventually they put them all together to formulate the code, right? The only thing that is the only problem is that the code that they gave us is actually in Python 2, but since we are switching to Python 3, so that we need to make a few modifications for the code that they generated. But anyway, we can still try this, right? So this time let me just first we can just start to like by using this to generate the Python code, we can start to write our own exploit script. So first what I'm going to do is that I'm going to copy this attack.py to attack2.py. So this attack2 is actually just a copy of this attack one, right? So and then let's take a look at this attack2.py. Okay, so this is actually the exactly same files, the one that I did for the first program, right? For the first ROP program, and we actually need to delete it, right? And we need to make, of course, we need to first make a few modifications. First, this time we actually target this ROP2 as the binary program, and then we need to create a payload, right? So the payload this time we can just first create and then copy paste all the stuff that shows here, right? Starting from this from stack import tag, right? So we can just copy paste everything that shows here into this program, and because they actually have some indentation issues, but we can fix this, right? So we can just make sure that the indentation is on the same level, right? And also this from struct import pack should be putting at the top, right? So we just put it at the top. Okay. So that's pretty much how to like utilize the generated code. You can see I already put all this memory address into it. And because, as I mentioned, this is the code that written in Python 2, we need to convert it into Python 3. So we need to make a few modifications. The first modification is that we need to adding this B at the front of these two lines, right? So adding extra B at the front of these two lines to convert this as a byte. This is actually a new kind of requirement for Python 3 only, right? You don't have to do that for Python 2. And then, of course, delete this one. Another thing that I can see is that our program, our old program, we named this process as P, and then this the auto-generated one called this payload as P. So therefore, they are actually gonna make a confliction. So we need to change all the this old payload, this I mean the process P into another name. So we can call that PROC as process, right? So of course this time we need to change this p.send to be PROC process send PROC, and also because the automatic generator one call this one P instead of payload, so we just call that send P, right? All right, so that's basically the logic. Well, it's like this. First we create a we just say start a process targeting to ROP2 that program, and then we name it PROC proc, and then we copy paste the payload that automatically generated by this ROP gadget, and then send it, and then turn it into interactive. Oh, there's one more thing we need to do is that all this payload is just assume that we already successful launched the buffer overflow attack. So that means here on the top you still need to find out the magic number. So we still need to find using some because it says paddings goes here, right? So we actually need to write our paddings. So this paddings should be like a times something, right? So we still need to find out the magic number to trigger buffer overflow. So that means in order to find this magic numbers, we still need to use GDB, and then this time we run the program, and then putting the deep region or cyclic buffer string into it, right? And then they can trigger this buffer overflow. Well, it seems that this time it's not triggered. So let me just I mean, probably it's because the string is just not big enough, right? So that's pretty much because the string is not big enough. So in that case, we need to use GDB to create another string, right? So this time we do this pattern create 200, right? So let's make it a little bit bigger, and then they're gonna generate a pattern for 200 strings, because previously I think that the pattern is 150, which is not good enough for triggering this buffer overflow. And then once they create it, then this time we can create a new files called string 200, and then we just paste the string in it, right? And once we paste the string in it, this time we can go back and rerun this GDB until analysis ROP2. And this time, once we run this program by typing R, we can redirect this string 200 in it. And this time, as you can see, we successfully crashed the program. And then inside the EIP, there is actually a string in it. So you can using pattern search and then type this $EIP. It's gonna tells me that the magic number is most likely 148. So that is indeed the magic number that we are looking for. And then finally we can just type a times 148. That's going to be the magic number, right? And I think we need to adding similarly, because the restrictions of Python 3 need to adding extra b at every single string, right? So to make this one as a byte, right? So and then the rest of the part should be the same. So BA and then B bin and bin BSH, right? So to mark it as byte string. Anyway, so hopefully this time we can successfully launch this attack. So we can write Python 3 attack2.py, and then it's the moment of truth. Let's see whether if we got the shell. Okay, finally we successfully launch the attack and we get the shell, right? So you can see that who am I, and then they can print out. So as you can see, this let me just quickly show you what I did, right? So in this example, I'm not using any functions that like predefined functions. Instead, in this example, we actually use this ROP gadget to help us to find out all the available gadgets and placing them together to launch a system call, right? So the system call is actually just putting all the values into EAX, and then eventually once they call this interrupt 0x80, of course they need to find the shell that the gadget allows us to do that. Once we're placing everything together, eventually they simply just calling this bin sh, launch a system call, and calling this command, and then we got the shell, right? So this is of course this is actually more generalized solution. It will works for any type of ROP project, right? I mean, for any program that has this ROP vulnerability, right? As if we can gather enough gadget, then we can launch this type of attack. All right, so that's all for today. That's in today's lecture. I shows you this return-oriented programming attack, right? And first I shows you the concept, and then I shows you 2 examples. And I'm going to post a lab 3. The lab 3 will be available very soon. And in lab 3, you are going to like redo what I did for the first lab. So for the first example, this one, right? So we're going to calling several functions and then passing argument. But this time the program will be a little bit, the structure of the program might be a little bit different. So you cannot like reuse exactly the same code, but very similar to this example, right? And so that's pretty much all for today. And thanks for watching. See you guys next week.